So this quantitative force problem that I gave you as an extra one in class, so you may not have seen this yet. You can look at it tomorrow or today, which is Friday. So I've already drawn the force diagram just to save a little time and you listening to me talking. But kind of pulling all of the information from the problem up here. So kind of pulling everything from up here. So we're pulling a 40 kilogram box with a force of 165 Newton along a rope at an angle of 60 degrees. Frictional force is 15. So I drew my force diagram. So I have the actual applied force here, which is 165, so my blue arrow. I drew the components in, which you should always do. Draw in the X component of the applied force and the Y. So I have those there in black. And then force of gravity, always acting on the object straight down. Friction, we know is 15, so we can put that value there already. And then I always, again, my box is being supported by the floor, so I should have a normal force acting upward. Now, I'm not going to go, really all we need to be able to do is like get all of the other values on the force diagram. So I think some of the stuff that was written that you can kind of see on the bottom of this page might be just, it's helpful if you kind of are struggling to understand it, but if you get it, just kind of go with it and just fill in all the other values on the force diagram. So if I switch pages here, so there's our force diagram copied over again. So one thing I can always do is calculate the force of gravity, which is my mass times the gravitational field strength of 10. So in this case, that's 40 times 10, which is 400 newtons. I know that's my force of gravity. Now, that tells me that. That's the only thing it really tells me, because the only problem is the force of gravity has to equal the Y component plus the normal force. So I don't know these two values here. I don't know these two values, so I can't really do anything with the force of gravity. It's not really equal to anything by itself. But what I can do is start to calculate the other components of the forces. So let's just start with the X component here, which runs adjacent to the angle of 60 degrees. So that way, and I have the hypotenuse, so I can use cosine to solve for that. So cosine of 60, which is equal to the Y component, sorry, not the Y component, the X component over 165. And then to solve for the X component, that tells me that cosine of 60 times 165 would be X, which would be 82.5. So that would be my value there. So the X, I can then add that to my force diagram, which would be 82.5 newtons, acting to the right for the X component. Now as I continue, so now I can calculate my Y component as well. So in this case, that would be sine of 60. It's going to be sine because this is my opposite side. I'm just going to use the hypotenuse again, so sine of 60 is what we would use there. So sine of 60 is equal to, oh, I did it again, the Y over 165. Then to solve for Y, I need to multiply by both sides by 165. So 165 times cosine of, or sorry, times sine of 60, which would equal 142.9 when you punch that into a calculator. So 142.9. So that tells me my Y component is 142.9 newtons. Now, the only thing I don't have on my force diagram is my normal force, which again, my normal force kind of in this equation here is the Y component plus the normal force is equal to gravity. So to find the normal force, I just need to subtract this Y component by gravity. And I've kind of run out of room, so I'm just going to show that up here and write so 257.1. I also forgot a stylus at school, so that's why this looks so terrible. But 257.1 newtons would be your normal force, because again, the y component, so here this 142.9 and the normal force together, so these two together have to equal gravity, which is 400 newtons. So kind of working through the problem in that fashion. Now looking at another problem from today that you got kind of in the pages of problems on paper. So we have the children being pulled in a wagon. The total mass of the wagon and the kids is 120 kilograms. Applies a force of 180 newtons on the handle, and the wagon speeds up. The frictional force acting on the block is 15 newtons. So now drawing in our force diagram here. So again, we have the applied force acting up and to the right. We have the x component of the applied force and the y component of the applied force here. Friction, normal force acting upward, and the force of gravity acting downward. So again, I'm going to work through this problem on the next page. So again, similar force diagram, or the same force diagram we had on the previous page. So first thing we can always do is calculate the force of gravity, which again, our mass was 120 kilograms. So we take the mass times 10, which gives me 1,200 newtons of gravitational force. Now, that's all we can do with that right now, again, because upward we have, I'm going to draw it up here so I have more room this time. The force of gravity has to equal the normal force plus that y component. So we can't really do anything with force of gravity other than we know that it is 1,200 newtons. And we know since the thing is speeding up, the wagon, the x component here is going to have to be greater than friction, which that'll be easy to figure out. So let's go straight to this triangle now. We have a 50-degree angle. We have the hypotenuse of 180. So I'm going to go ahead and calculate the y component first. So y is opposite, so it's straight across from the angle. So I can take the y component, which will be sine of 50, which will be equal to the y over 180. So then to solve for y would be sine of 50 times 180, which would equal about 137.9 newtons. So there's my value for the y component. So I can go ahead and add that back to my force diagram. So I have 137.9 newtons of force. Now I'm going to keep adding and kind of work with the x component now. So my x component, which runs along that 50-degree angle, right along it here. So I'm going to use cosine. So cosine of 50 is equal to x over 180. You could use tangent if you want to. I just like using cosine just because it's a nice whole number of 180 for the hypotenuse. So then x equals cosine of 50 times 180. So that tells me my x is equal to 115.7. So it comes out to be greater than the frictional force, which makes sense because it needs to speed up. So 115.7. So we have that there, 1.15.7. And the last thing we need to do is again kind of get the normal force, which we can use this kind of thought up here that everything down, the force of gravity, has to equal everything up, which would be my normal force and this y component over here. So in that case, if I did that math, and I don't really have room to show it still. I can show it down here. The force of gravity minus the y component equals my normal force. So 1,200 minus 137.9, which equals 1062.1 newtons. So I can add that 1060. Oh geez, really should have brought the stylus on. 1062.1 newtons. We'd have that there, okay. And then that kind of completes my force diagram. So I have all of my forces calculated. I'm good to go. And I can calculate my net force taking this x component, 115.7 minus this, and that tells me how the net force acting on the actual wagon. And the last one, just go through a vertical example for everyone again. So we have a child who's in an elevator that is moving downward and speeding up at a rate of 2.4 meters per second squared. Now, again, you don't have to do this. I think it's a good idea, though. It's just kind of saying, okay, direction, acceleration, and net force, because those are the things we have to think about before we do anything else when we look at these problems. So, let's start here. So we have a child in an elevator. We're going to have the force of gravity and the normal force. We need to kind of decide which force is going to be greater in this situation. So, elevator is moving down, so that's my direction. I'm going down. I'm speeding up, which tells me that my speeding up rule is, if I'm speeding up, the direction the object is moving, here, so this, has to be the same as the acceleration. They have to be in the same direction. If we're slowing down, they're opposite. So in this case, we're speeding up. So again, they have to be the same. These two have to be the same if the object is speeding up. Now, if, with that known, the acceleration we know has to always be in the same direction. So these two are always in the same direction. Same direction if they're speeding up, opposite direction if these are if it's slowing down. Okay, but we're speeding up, and the acceleration must be net force. So that means our downward force has to be greater, because we have to. Our force diagram needs to be unbalanced in the downward direction, meaning the downward force has to be greater than. So in that case, my force of gravity has to be greater than the normal force. I can just show that. How much greater we don't know yet, but I can just show that here. So, next thing we can always do is we can calculate the force of gravity. So force of gravity, mass times the gravitational field strength of 10. So in this case, would be 30 times 10, which equals 300 newtons. So 300 newtons. Now, the other thing we need to do then is we need to figure out, we know that the gravity has to be greater, but we don't know how much greater. So we need to calculate the net force. So net force is equal to mass times acceleration. So in this case, 30 times 2.4 newton, or 2.4 meters per second squared, which when I do that math, I get 72. So the net force is 72 newtons. That is not the normal force. That tells me how much different the normal force needs to be than the force of gravity. So here, so we need to subtract those values. So the normal force is equal to gravity minus the net force, which is 300 minus 72, which would give me a normal force of 228 newtons. So again, the force has to be 72 because we need an unbalancedness of 72 newtons.